Hello everyone, this is Pruthvi Chaitanya, and today I am going to give an overview on my research topic DC bus voltage regulation and decentralized control of parallel inverters in an islanded hybrid microgrid system. It's a part of UI Assist student webinar series, and I have done my BTech in electrical engineering from JNTU Hyderabad in 2012 and MTech in Power Electronics and Drives from NIT Rourkela in 2015. And I'm currently pursuing my PhD under the guidance of Professor Mahesh Kumar Mishra at IIT Madras. We shall begin today's topic with a quick overview and classification of hybrid microgrid system. And from there, we will move on to the design of AC bus controller and then DC bus controller with a suitable control strategy to address few operational challenges in the system and then discuss some concluding remarks. So, a typical hybrid microgrid system structure is shown in figure 1, which gives the advantages of both AC electric system and the DC electric system. It may use energy sources like wind, solar, fuel cell, diesel generator, and energy storage system like supercapacitor and battery units to basically address the intermittent nature of the renewable energy sources. And the distributed AC and DC loads are connected to the respective buses. Interfacing converters are used to share power among the buses. That is, to share power in bidirectional power flow will happen at the AC bus and DC bus. And also, all these power sources are connected to their respective buses through appropriate power electronic converters. Based on how these power sources are connected, the hybrid microgrid is classified into three types. If sources are connected to both AC bus and DC bus, then it is called a DC AC coupled hybrid microgrid. Similarly, if all the power sources are connected to AC bus alone and DC bus is an extension of AC grid, it is called as AC coupled hybrid microgrid, as shown in this figure. All the power sources like wind, PV, battery, supercapacitor units are connected to the AC bus alone, and DC bus is formed as an extension of AC bus through AC to DC converter. Similarly, if all the power sources are connected to the DC bus alone, and AC bus is formed through through interfacing converters. Here, DC to AC converters along with some filter section is forming the AC bus. So this kind of system is called DC coupled hybrid microgrid system. In all the three cases, if the microgrid is connected to the utility grid, then it will be operated in grid connected mode. Otherwise, it will be operated in islanded mode, or also called as autonomous mode of operation. So, if you see few challenges in the system considered, then at the DC bus, the challenge is like power balancing, which because in it is having various power sources, there will be a mismatch of power when the load changes are occurring. Also, there will be a change of voltage at the DC bus. So the DC link voltage control and power balancing is an important aspect. Similarly, if multiple sources are connected at the AC bus, then first thing is we have to bring it into operation. For that, synchronization of various voltage source inverters is one more challenge. Then control strategy and power management at the AC bus, that includes voltage regulation, frequency regulation, real-time power dispatching among different power sources is another challenge. And when we are operating renewable energy sources in a microgrid, and when we are bringing it into operation in a grid connected mode, then the major disadvantage is like it will not be having any inertial behavior compared to conventional power system. So bringing a dynamic performance or improving the dynamic performance of microgrid, that includes initial response and damping out of the power oscillations, is one more challenge. So in order to address a few challenges of these, a simple PV, battery, and supercapacitor based system is considered in the study. Here we are confining our discussion to a islanded hybrid microgrid system, that to be a DC coupled hybrid microgrid system. In this, PV system is connected to the DC bus through a boost converter. And battery and supercapacitor based energy storage system is connected to the DC bus through bidirectional converters. And the DC bus is common to both inverters, means two inverters are connected in parallel, and these parallel inverters are forming the AC bus using LCL filter section. So the advantage of this system is these parallel inverters we can add or remove based on the requirement. That is, it is easily scalable, and when we are connecting in parallel, the basic advantage is redundancy. So and also we can meet the high power applications using lower rating of the switches. And we are considering a battery and supercapacitor based hybrid energy storage system, which is nothing but a high energy density, that is nothing but battery, and high power density unit, that is supercapacitor. The combination is having certain advantages, which we are going to see in coming slides. We'll take few queries then. And before that, the major focus of the work uh, is to fast restoration of the DC link voltage using AC plus frequency variations. That means for that we are using uh, a droop control. That's why these frequency changes are coming. So in short, we are dividing the work into three parts. That is execution of droop control in parallel inverters for real-time power dispatch, because this will not be having any external communication channels. So, but it will bring some frequency changes. Okay, then using those frequency changes and hybrid energy storage system, we will regulate the DC link voltage. These frequency changes are nothing but the indication of power mismatch between generation and load demand. That is, these frequency changes arises when there is a load change either at the DC bus or at the AC bus in the present system. And then finally, we'll restore the frequency to the nominal value, that is frequency regulation.
Droop control is a well-known technique in conventional power system. The similar technique is used to control output active and reactive powers of voltage source inverter. From figure 5 and 6, the droop control changes active and reactive powers of VSI by changing the frequency and output voltage according to equation 1 and 2. From these equations, P and Q are the active and reactive power outputs. MP and NQ are the droop coefficients. F reference and V reference are the reference frequency and voltages. And F and V are the actual frequency and voltage of the VSI. The droop coefficients are designed based on the inverter rated powers and allowed maximum deviations in frequency and voltage as per the grid code. So why we need a droop control? Because droop control doesn't need external communication channels, but local measurements like frequency and voltage, which eventually varies globally, are sufficient. Thus, it is a cost-effective solution. Also, it makes microgrid more scalable and expandable with redundant approach. When n inverters are connected in parallel with different ratings, at steady state, the inverters will share powers proportionately among themselves. That is, NP1 P1 equal to MP2 P2 equal to so on NPN PN. Here, MP is a power frequency droop coefficient. And because the droop coefficients are designed to be inversely proportional to their ratings, this happens. That is power sharing proportional to their ratings. Also, this equation is true. Its system's a steady state at which the inverter's frequency may be different from the rated frequency, but in order to execute the droop control, the active and reactive powers must be decoupled. To understand this, consider a voltage source inverter as shown in figure 7, which is having an output voltage of V01 angle delta and PCC voltage of V angle 0. And from this, power delivery equations can be written as P is approximately equal to V01 into V by X sine delta, and Q is approximately equal to V by X into V01 minus V. Means from this, for smaller values of delta, P is directly proportional to delta, which in turn is proportional to frequency. And Q is directly proportional to V01 minus V, that is the voltage difference between terminal voltage and PCC voltage. So this equation is possible only in an inductive output impedance network. If the output impedance changes are unknown, system behavior will not be as desired. So this problem can be overcome by emulating virtual inductive impedance in the control strategy. Here the emulation means we are controlling the terminal voltage V01 such that it gives a desired current I0 in a closed loop control by satisfying the equation L into di by dt equal to V01 minus V. This voltage drop is a voltage drop across a virtual inductance L wedge. So we are treating it as a V virtual and it is represented in ABC frame. When we convert it into DQ frame with a suitable orientation, then equation 3 and 4 are arrived. And from these equations, we can see the rate of change of currents di naught d by dt, di naught q by dt. So to measure these currents, we are using a low pass filter GL of S, which is fed with input currents I naught D, I naught Q, and the output currents are treated as I naught D filter and I naught Q filter. And using Taylor series of expansion, we can measure the di naught d by dt by neglecting the higher order terms. This 5 and 6 are converged to. And substituting these 5 and 6 in equations 3 and 4, we end up with the voltage drop across the virtual inductance, that is Vd virtual and Vq virtual, from these equations. So the overall decentralized control scheme will be appearing like this. We will take the instantaneous terminal voltage of V01 and current I0, and they will convert it into DQ frame, and we fed to measure the instantaneous active and reactive powers. And these are sent through a low pass filter to extract the average active and reactive powers, and then implemented the Droop characteristics to get a reference frequency and reference voltage. And with the measured terminal currents I0 D, I0 Q, we are modifying the reference voltage such that to emulate the virtual inductance behavior. So finally, the reference voltages are V01 star, V01 D star, and V01 Q star. And we are extracting the plant D-axis model and Q-axis model. The plant is nothing but a switching inverter and LCL filter connections. From these, we are extracting the plant D-axis model, and a two-loop control strategy is used. That is outer voltage control loop and inner current control loop. And in that, the reference voltage and the actual voltage are compared and fed to a PI controller, whose output is taken as the current reference. And this current reference compared with actual current and fed to a PI controller, from where we are switching using a PWM technique, and that is generating the output voltage. And these are the AC bus system parameters that we are using. Also in the previous slide here, the PI control parameters are suitably designed and kept. That is for a switching frequency of 10 kilohertz, the inner controller bandwidth is considered as 1 kilohertz, and outer voltage controller loop bandwidth is taken as 100 hertz. And these are the system parameters with a nominal voltage of 110 volts line to line, and nominal frequency is 50 hertz, and switching frequency for the two inverters are 10 kilohertz. And the inverter side filter parameters and virtual inductance value, Droop coefficients, means two loads are considered here. One is RL load and another one is R load, and those values are given, and voltage controller and current controller bandwidth and parameters are specified here. From this, and one more thing is here the inverters are considered or treated in two different ratings, that is 1 kVA and 2 kVA inverters. That is, it is meant to show the effectiveness of the Droop control that we are going to implement. Means the power sharing ratio should be 1:2 because their ratings are in the ratio of 1:2. So finally, this secondary control, that is frequency regulation, means here we are using the same frequency power Droop characteristic, that is F equal to F reference minus MP into P, to regulate the frequency. From this equation, MP is a constant, and during the load disturbance or load changes, power imbalance occurs. Those power imbalance will be reflected in active power output delivered. So based on the power variation, we will vary the frequency such that F is a function of active power alone. That means during the load disturbance, we are treating F reference and MP as constants, and we are varying the frequency. For a change in power from P to P dash, the frequency will be varying from some F reference to F dash, and the delta F is an indication of change in power delta P. Similarly, once it reaches the steady state, which is measured using two delay stages or two delay control units, we are treating the P as a constant because its steady state power is not varying. So P is treated as constant from this equation. And F reference is varied such that F is equal to F rated. That means during the steady state, F will act as a function of F reference alone. From these, we will regulate the frequency to nominal value. So with these two control strategies, the overall control of AC bus will be converged as shown in figure 12. It consists of outer frequency regulation loop where F reference command is based on the steady state achievement. And then in the next to that loop, we are having a PQ calculation and Droop control loop, means it is the outer power loop we can call, through which we are generating V01 and F. And after modifying the value of voltage such that it is implementing the making the output impedance to be inductive, we are getting a reference voltage of V01 star and a frequency of F star. From this, we are generating a ABC frame based voltage signal using sine function generator that is converted into DQ frame and fed to the voltage controller loop and then to the current control loop. Through this, we are generating some duty signal, and that is fed to the inverter, and a sinusoidal PWM switching scheme is used here. That's how we are achieving a terminal voltage of V01 angle delta. This is how the VSI forming the AC bus is designed and controlled. Then we will move on to the DC bus system specifications. This is the DC bus system parameters. It is designed for 210 volts as nominal voltage and rated for 1500 watts with a DC link capacitance as 3300 microfarads. PV system is emulated using regulated power supply, assuming that it is operated at MPP, that is maximum power point. With the listed specification, that is 120 volts 10 amperes, we are emulating the PV system. Then we are using a lead acid battery pack of 26 ampere hour and 108 volts, and supercapacitor pack of 8.28 farads and 84 volts as a nominal voltage is considered. Though PV, battery and supercapacitor units are forming the DC bus, energy storage system alone is operated in voltage control mode, and the PV system based boost converter is operated in current control mode, and the voltage control mode is meant to regulate the DC link voltage. That means energy storage system is kept for regulating the DC link voltage. The bidirectional converters are designed in boost control mode of operation, and the small signal model of the converters are given in figure 13. Means battery and supercapacitor units are operated in parallel to regulate the DC link voltage VDC. And here also a two loop control strategy is used. And the small signal model, various transfer functions like current to duty and voltage to current are shown in the slide. GCI, GCV are representing the PI controller parameters with a gain of GCI and GCV. Here, VDC is taken as a feedback and compared with the reference voltage VD star, that is 210 volts, and it is fed to the PI controller, and the output is treated as a current signal, and this current signal is passed through a low pass filter to extract the average and oscillating components or time varying components, and the average value is fed to the battery loop, and the oscillating component or time varying component is fed as a reference to the supercapacitor loop, and this current is tracked through a battery current control loop and fed means such that IB is equal to IB star, that is IDC average. Similarly, ISC is tracked such that it is equal to ISC star, that is IDC tilde. And these two are converted back and to voltage signal and fed to the PWM. and such that we are generating a DC link voltage of VDC equal to VDC star. And through the specified system parameters, we are have, because it is operated in boost control mode, and the boost converter uh, is having a right half plane 0, and that 0 is located at 74.4 radians per second. Here, the current control loop is having a current controller GCI of S. It is designed with a bandwidth of 3 kHz for battery converter and 5 kHz for the supercapacitor converter, because supercapacitor can release the power faster. And the controller 0 is located at 1/20th of the controller bandwidth. That is, here it is switching with a switching frequency of 10 kilohertz. So the accordingly the current controller bandwidth for a suitable current controller bandwidth 0 is located at, and the overall compensated loop gain, or means the Bode plot corresponding to closed loop control of the supercapacitor and closed loop control of the battery are shown in this figure, and the phase margin is achieved at 87.1 degrees. Similarly, the voltage controller bandwidth is chosen as 1/10 of the right half plane 0, which is located at 74.4 radians per second. And the controller 0 is placed at 1/10th of the bandwidth. And the corresponding Bode plots are shown in this figure. This TUV is representing the uncompensated plot, and TCV is the closed loop control plot with the compensation. And then from these calculations, the overall voltage control bandwidth is found to be 11 hertz, which is very low for the application, for our application. Because there are certain disadvantages with the lower controller bandwidth, because during the load changes, the poor bandwidth causes a significant voltage dip at the DC bus, which in turn is responsible for sluggish settling time. Also, the voltage deviation and slow restoration time will affect the critical loads connected across the DC grid and affect the modulation index of the VSA. That is voltage source inverter. Many methods are proposed to improve the controller bandwidth. Some of them are needed some auxiliary circuits. Some of them are very much complicated. But for the current decentralized control, that is Droop control based approach, it is in a simpler way we can improve the controller bandwidth, and to uh, that is in the hybrid microgrid system under study, using a feed forward control along with a feedback control, using the frequency changes aroused due to the Droop control, we are regulating the DC link voltage much faster. Hence, these frequency changes are an indication of power imbalance in the network.
In an alternator, the torque equation is given by delta tau equal to J into d by dt of delta omega plus d into delta omega. The change in power is given by delta P equal to J into omega naught into d by dt of delta omega plus d omega naught into delta omega. Here J is the moment of inertia and d is damping constant. In this, the first part is called as inertial power, that is J omega naught into d by dt of delta omega, and the second part is called damping power, that is d omega naught into delta omega. And the inertia constant is defined as h equal to half J omega naught square by S, where S is the rating of the alternator. From this knowledge, the change in frequency is relevant or equal to the load disturbance or power imbalance. Applying this knowledge in group controlled VSI, we have the load variation causes power imbalance between generation and demand. This is momentarily adjusted by DC link capacitance by drooping or raising the DC link voltage. Later, power balance is achieved by controlling the storage system, which regulates the DC link voltage. And in whole process, the power variations are indicated using frequency changes through the knowledge of droop characteristics. At steady state, the frequency is 50 Hz, therefore delta F equal to 0. But at low disturbance, it is an indication of power imbalance. And this is equal to delta F by MP as shown here. and this is named as damping power. Once this power is calculated, it is converted into its equivalent current. That is, P damp is converted into I damp, and this current is sent through a low pass filter to extract the average and oscillating components as shown in figure 16. These are the feed forward terms to the DC link voltage regulator to pump the additional power required at the DC bus. Similar to the damping power, virtual inertia is emulated to the DC link, that is controlling the rate of change of DC link voltage by controlling power delivered or absorbed by the storage system proportional to the rate of change of frequency. And the equation goes like P inert, that is inertial power, is equal to 2h by f naught into d by dt of delta f. Here h is taken as 10, and as shown in figure, the average and oscillating powers are extracted, and these average power is fed as a reference to the battery, and the I inert is means oscillating component is fed as a reference to the supercapacitor. So orally, the small signal model of the proposed voltage regulator will appear like this. In this, the feedback and controller design is similar to the conventional approach, whereas these feed forward terms are additionally added to emulate the damping and inertial power. So the reference currents are modified such that IB star equal to IDC plus IDAMP plus I inert, ISC star equal to IDC, IDAMP and I inert, all are time varying components. From this, damping and inertial current terms are fed using feed-forward terms, which ensures effective utilization of energy storage system. In this, we are feeding average current to battery and time-varying component to the supercapacitor so that the stress on the battery will be reduced, which increases its lifetime. That is, battery's lifetime will be increased because the stress, the sudden changes or surges will be taken by the supercapacitor. So supercapacitor is effectively utilized because all the sudden transients are meant to be supplied by a storage system which is having high power density that is capable by supercapacitor. So from this we can have a question like how to select the battery units and supercapacitor units. Here we start with the battery unit selection. IEEE 485 2010 standard is used for sizing the lead acid battery. For this selection, we need a critical load and the backup duration. Here, 1/3 of the load is considered as a critical load, and the backup duration is considered for 12 hours. And the minimum allowed voltage across a battery unit, that is how far we can drop the voltage, is considered as a one more parameter. And then converter again total current requirement, and thereby selecting the number of series and parallel strings will be decided based on that. Once we have the selected batteries, then we have to go with ampere hour capacity of selection unit. That depends on the ampere and the backup duration, ampere the current requirement, peak current requirement, and backup duration. From there, based on the load characteristics, we will decide the C rating. So that's how we are from once we have all these calculations, then we'll check the commercial available batteries, and from there we will select suitable batteries. Coming to the supercapacitor units, we don't have any specific IEEE standard for sizing the supercapacitor units, unlike batteries. So in this application, supercapacitor units are used for addressing the transients for a duration of 1 minute. And selecting the maximum load requirement for transient power supply is an important parameter. From there, we will decide the transient duration that is taken as 1 minute here. And then from there, identifying the capacitance requirement from energy balancing equation, that is half CV square into means eta, that is efficiency, will come into picture. And the energy is nothing but power into time. So according to the backup duration, we will calculate the capacitance requirement. From there, we will connect number of series and parallel strings. And then we will check for the commercially available supercapacitors. And this is the overall experimental setup, which consists of DSpace 1202 and host system. And we use two semicron inverters of ratings 1 kVA and 2 kVA. and then various Hall effect sensors are used here, and the other components are marked in the figure. So these are the results. Uh, uh, from the figure 20, we can see that there are various load changing instances. That is, load 1 is connected at t equal to t1 seconds, and load 2 is connected at t equal to t3 seconds. And both the loads together removed at a t equal to t5 seconds, and at a t7 instance both the loads are added. These changes are according to the interest of showing the variations in battery, supercapacitor and PV currents, and the variations in DC link voltage. Here the peak load change is 750 watts, that is both RL and R loads at the AC bus site is connected, and a continuous DC load is presented throughout at the DC bus. And here from figure 20, we can see the variations in frequency of inverter 1 and inverter 2, and changes means output power supplied by the inverter 1 and inverter 2. So from this we can say this the power share, the inverters are sharing 70 watts, 140 watts at a load 1 instant, and 240 watts, 480 watts at load 2 instants. Means when load 1 and load 2 together are going on. So the and means at every instant the power sharing ratio is 1:2, which is equal to the uh, inverter ratings, and the frequencies also changed. Means as we are applying the Droop control, the frequencies are changing at every load instant, that is at T1, T3, T5 and T7, and the loads are falling to 49.96 hertz, 49.93 hertz and 50.1 hertz, and then 49.9 hertz respectively at every load change. Means the Droop control is implemented successfully, and at the same time the changes in PV, battery and supercapacitor currents and DC link voltage variations are shown in figure 21. Here the PV current is kept constant throughout the operation because we need to observe the changes in supercapacitor and battery, how are they responding, and the zoomed view is shown in figure 22. From this figure we can conclude that the supercapacitor is acting fastly and only during the transients, and the battery is taking the continuous steady state current, and the stress on the battery is reduced, and thereby the lifetime of the battery rate will be increased. And at the peak load change from figure 21, we can observe that at the peak load change, that is at 750 watts for a rating of 1500 watts of the DC bus, the DC link voltage dip is limited to 4 volts. To show the effectiveness of the proposed control strategy, we are comparing it with the conventional DC link controller, that is without any feed forward terms, that is shown in figure 25. That means at a peak load change, if we observe, the DC link voltage dip is it is fallen to 192 volts. That is around 18 volts dip is observed at 50% rated load change. And if it is operated at the rated load condition, then it would be further increases. And based on the dip, the settling time is also has taken up to 2200 milliseconds. This can also be reduced further. So from whereas with the proposed control strategy, the dip is adjusted to 4 volts and the settling time is 60 milliseconds. So overall, the voltage dip is reduced by 72% at a considered peak load change, and the settling time is almost some 3 cycles with respect to AC set frequency. So coming to the conclusion, this proposed method uses reference currents generated using feed-forward terms, which are calculated and updated using frequency variations, and it does not require any bandwidth-limited voltage controller. Means when it is with respect to feed-forward control, then the feedback loop controller bandwidth has no significance, and the AC bus frequency is regulated without using any additional PI controllers. Also, the battery supercapacitor combination based hybrid energy storage system is effectively utilized for providing inertia to the DC link and for power balancing in the islanded hybrid microgrid system. These are the few references. Thank you.